dipole moment, and the other one is inductive effect. Dipole moment, I hope all of you are very much familiar with this term, that is the separation of charges in a polar covalent creates a dipole. This term is most probably are usually used for covalent molecules because in ionic compounds there is a remarkable separation of positive and negative charges, and those positive and negative charges are attached to each other through electrostatic force of attraction. But in covalent bond, molecules are attached with each other due to sharing of their valence shell electrons, and it depends upon their electronegativity. The most electronegative atom shared attracts shared pair of electrons towards itself and creates more negative charge on it, and the other part of the molecule have a positive charge. The word dipole means two poles and refers to the positive and negative poles or ends that result from the separation of charges within a molecule. And this dipole creates a net dipole moment in a molecule, and it is a factor or a source for the production of polarity in a molecule. Definitely, this is a property that is responsible for various type of reactions, applications of a molecule. So we must know polarity of a molecule. In so many daily life applications and in industrial applications, in medical applications, polarity, knowledge of polarity is very much important. So many medicines you are using at your home that you get after the prescription of a doctor. Same medicine sometimes you can get in a syrup form, in a tablet form, and in a capsule. All of these three different forms can be produced after the proper knowledge of dipole moment of a molecule. If you know a dipole moment of a molecule and you want to completely dissolve that molecule, then you shall take a solvent of exactly similar dipole moment. All of you are very much familiar with the principle that like dissolve like. So this is represented by a Greek word mu, which is a measure of magnitude of separated charges and distance between them. The proper definition for the term dipole moment is product of magnitude of charges at either end and the distance between the center of gravity of positive and negative charge, and it is represented by mu is equal to q and q into d. The charges are very small, have small values, and their values are in 10 raised to power minus 10 ESU, and the distance is also in a very small number, that is 10 raised to power minus 8 centimeter. So the usual magnitude of dipole moment is in the order of 10 raised to power minus 18. Means if the separation of charges on both of the molecule is unity and the average distance between different dipolar molecule is 10 raised to power minus 10, the product of charge and distance will become is equal to 10 raised to power minus ESU centimeter. So this very small unit is not convenient to use in your numerical applications, because when you are using this dipole moment and you want to find a proper solvent, so the utilization of these smaller units is not easy. The best way is to convert these type of units into whole numbers. All of you are familiar with pH. In previous classes you have studied that pH is hydrogen ion concentration is usually in 10 raised to power minus 7 minus 4. The solution to convert that number 10 raised to power minus 4, 10 raised to power minus 10, that was derived by Sorensen, that take negative log of that number. By taking negative log, the figure that is in exponential form minus 4 minus 10 will become coefficient after taking negative log. This is a very common approach in sciences and mathematics to convert decimal quantity into whole numbers. So for the conversion of this small unit, the alternative unit was used as dBi. dBi is abbreviated as d, and it's equal to 1 dBi is equal to 10 raised to power minus 10 raised to power 34 into 10 raised to power minus 30. Commonly unit used is dBi. The dipole moment for the molecule methyl chloride is, excuse me for a while, is 1.87 dBi. It's not possible to determine individual bond moment within a molecule. Let's suppose if a molecule has CHCl3. I am taking just a derivative of above mentioned molecule. This is CH3Cl, and the other molecule is CHCl3. So in the second case, the determination of each CCl bond is not possible because molecule is in a accumulated in form. By using any type of instrument, it's not possible to determine molecular dipole moment of a individual bond. We can determine only dipole moment of overall molecule. Direction of dipole moment, this is a vector quantity indicated by an arrow over a molecule pointing the negative charge. The value of individual bond moments are roughly the same in all molecules. Individual bond moments are therefore can be used to calculate expected dipole moment of molecule. This is a very interesting example. Here we have mentioned three examples. First one is toluene, which has a methyl group attached to a benzene. Its dipole moment is 0.43 dBi. The other one is nitrobenzene. Its dipole moment is also in the same direction, and its dipole moment is 3.93 dBi. So in the third example, we have these similar groups and attached at the same position but within the same molecule. So we are expecting that its dipole moment should be equal to 0.43 plus 3.39. So when practically its dipole moment was determined, it was very close to the expected dipole moment, that is expected was 4.36 dBi and actual value was 4.39, and this is not very this is very much close to our expected value. So the next one, when many molecules have a polar bond, do not exhibit dipole moment because their individual bond moments are so oriented that they cancel the effect of each other. You can see the example of carbon dioxide. If you take one bond of carbon with oxygen, it's a polar molecule. A polar bond because oxygen is more electronegative, and at the left side oxygen is also electronegative, but they are equal in force and attracting in opposite directions. That's why these vector values cancel out effect of each other, and overall dipole moment for the molecule of carbon dioxide will be observed as 0. Similarly, trans 1 to dichloroethylene. We have two molecules having similar groups, but their position in space is different. The molecule at the left hand side has two chloro groups. They are opposite in direction, and we know that when two similar groups are in opposite direction, the molecule is known as trans. And the second one, that is at the right hand side, molecule has two chloro groups at the downside. So at the first molecule, these chloro groups are in a position to cancel out their dipole moment, and net effect will be observed as molecule will be having 0 dipole moment. But in case of cis molecule, the molecule is a polar molecule and it has a value of dipole moment. Similarly, dipole moment for CCl4 will be 0, CH4 will be 0, para dinitrobenzene is 0 because in para dinitrobenzene both of two nitro groups are in position at 1 and 4. In general, the dipole moment is a measure of polarity of a molecule. The greater the value of dipole moment, the greater is the polarity of molecule. So this is the end of this topic. Now I am going to switch our second topic of the day, that is inductive effect. What is inductive effect? Inductive effect is, as you know, induced. The word induced is something like being produced forcefully. It is not the actual effect of that atom or bond. It is the effect produced by some neighboring group or neighboring atom. The inductive effect of a group of atoms is a change in electron density at the nearby atom caused by difference in electronegativity. Inductive effect can be electron releasing and electron withdrawing. This means sometimes the group attached to the neighbors can donate their electron density, and the other case also exists. Sometimes the molecule can withdraw electron density from the neighbors. So how can we determine whether an atom or a group of atom will donate electron density to the neighbors, or it will withdraw electron density from the neighbors? So this is a very simple criteria to keep in mind. You have to take your notebook and note my these words. If an electronegative atom is neutral or it has a positive charge, it will withdraw electron density from the neighbors. And the second case, if an electronegative atom has positive charge, it will withdraw electron density from the neighbors. I'm going to repeat these lines. Electronegative atom, either it's negative or it's neutral, it will donate electron density to the neighbors. The second case is, if the electronegative atom is positively charged, it will withdraw electron density from neighbors. I'm not going into detail of this alpha and beta carbons because you will understand these lines by taking information from the next slide. In this case, at the bottom you have two examples, that is ethyl chloride, and the other one is ethyl group attached to a quaternary ammonium ion. I was talking in my previous slide that polarity. Now I am going to tell you about the definition of dipole moment. You have also take your notebook and note these lines. Polarity. So before going into definition, I will tell you. You are watching at the screen. One carbon is CH2 and the other one is CH3. Both of these carbons are sp3 hybridized. It means they are having same electronegativity. For a while, if we hide bond of CH2 with Cl, for the time being, we are just talking about the bond between CH3 and CH2. Both of these carbons are sp3 hybridized and they are having same electronegativity, and their shared pair of electrons should be at the center of these two carbons. This bond should be non-polar in nature. Alright, now we hide CH3 and we take the case of CH2 and Cl. The bond between Cl and CH2 should be polar, and it's polar because chlorine is more electronegative as compared to CH2, so it will withdraw shared pair of electron from carbon, so there will be a production of partial positive charge on carbon. So it's natural phenomenon. None of the species in the nature likes to carry a positive or negative charge. It tries to nullify the effect of charge. So what will do this CH2? This CH2 will withdraw electrons from CH3. Individually, CH2-CH3 bond is nonpolar, CH2-Cl bond is nonpolar, but both of these bonds are in single molecule. So Cl group induces polarity in CH2-CH3 bond. This is inductive effect. Polarity. Now you can take your copy and pencil and write the definition of inductive effect. Polarity induced in a nonpolar bond due to an adjacent polar bond is known as inductive effect. And at the right side, I I think so. One thing I explained very wrong, and I put very much emphasis on that description of electron donating and withdrawing effect, and hope so that that explanation is set in your mind, and it will take some time to delete my words from your minds. uh, Electronegative atom, if it is a neutral or positively charged, it will withdraw electron density from the neighbors. An electronegative atom, if it is negatively charged, it will donate electron density to the neighbors. In my previous slide, I put a large emphasis while discussing about the classification of groups which are electron donating and electron withdrawing. So you have to delete those words from your mind, and you have to uh, restore these words, that electronegative atom, when it's neutral and positively charged, it will withdraw electron density, and if it is negatively charged, then it can donate electron density to the neighbors. And the other case, that is electron donating, that is any alkyl group. Why alkyl group has electron donating inductive effect? This can be explained in some other topic that is known as hyperconjugation. I'm very sorry that I put a large emphasis in my previous slide while describing about electron donating and electron withdrawing effect. So this is a video lecture, so I cannot go back and delete those words from the video. You have to take into consideration my discussion that I'm going to deliver at this moment. So this is the case in which an electronegative atom has negative charge and it is attached to an adjacent group. So it is donating electron density to the neighbors. So here is the classification that I discussed two times. Once it went wrong, and the second time it was right discussion. So you can see at the bottom electron withdrawing groups, that electronegative atom having positive charge, nitrogen in Nr3 and NH3, that is positively charged. In case of NO2, usually nitrogen in NO2 group, with one oxygen it is attached through double bond, and to the second oxygen it is attached through coordinate covalent bond. That's why in this case nitrogen has positive charge. In cyanide, in carboxylate ions, all the electronegative atoms like fluorine, chlorine, iodine, these are OH is very important group. So all of these groups are electron withdrawing groups. And electron donating group, when electronegative atom has a negative charge, it will donate electron density. And all the alkyl groups, whether it is tertiary alkyl group, that is R3C, secondary alkyl group R2CH, and primary alkyl group, that is CH3. Alkyl groups have usually been regarded as electron donating, but in recent years many examples have been found that their behavior in some cases is best explained by positive and negative in relative to hydrogen depending upon the situation. So one thing that is very important that we can derive from this point. So how can we describe whether a group is electron donating or electron withdrawing. What is the criteria for the measurement? The criteria is very simple. For the measurement of inductive effect, we cannot have absolute value. We can measure inductive effect with reference to hydrogen. This is a time to understand about absolute value and reference value. If I say that what is the distance of Islamabad? So you will everybody in their own city will think that the distance of Islamabad is being asked from their own city. But I haven't mentioned that from which point to which point. For the value for which we are in need of a reference point is known as a relative value. Distance is a relative value. We cannot say Islamabad is 100 kilometer, Islamabad is 400 kilometer. We have to mention one reference point. For the description of distance, we always need a reference point. We can say Islamabad is 360 km from Lahore. Islamabad is 100 km from Jhelum, 200 km from Sialkot. So for the values for which we need a reference point, they are known as relative values. And the values for which we don't need any reference, they are known as absolute values. Like weight 1 kg, 2 kg, 3 kg. We don't need any reference value. For the height of a person, that may be for boys can start from 5.6 to 5.11, and maybe some guys are very tall, they may be 6 feet and more. And for the girls, the height is 5.3, 5.2, 5.4. So height, weight, these are absolute values, but the distance is a relative value because we need a reference point to describe distance. Similarly, inductive effect is a reference value. Here, there are few examples that chloroacetic acid is about 100 times as compared to acetic acid. Okay, chloroacetate. So I am going to discuss these points in my next slide. Here, but for more discussion, I have write down few examples for your better understanding. So that's why I'm going to my slide. Here I have written 6 examples. I skipped that slides because in this page I wrote all the examples in a very proper sequence. But it doesn't mean that you have to skip the previous slides. The discussion that I am going to tell you in this slide is described in previous slides. So after watching this slide, you have to take their description from previous slides. The first example is formic acid, second is acetic acid, third is fluoroacetic acid, four is difluoroacetic acid, fifth one is trifluoroacetic acid, and sixth one is 1, 2, 3. 3-fluoropropanoic acid. For the determination of acid strength, we always look for the stability of a conjugate base. If a conjugate base is stable, the respective acid will be stronger. Conjugate base stability means that conjugate base at the right hand side that I have mentioned at the bottom of very first equation, conjugate base. Conjugate base stability mean that it will not give back reversible reaction. It will not capture proton to give reversible reaction because these reactions are reversible reactions and usually studied in aqueous media. In your first semester of BS, you have taken a course in organic chemistry. In that course, you have studied a lot about acidic and basic properties. So if a conjugate base is stable, it will not capture proton and it will not go reversible reaction. So it means in case of stable conjugate base, there will be a more number of protons and acid will be a stronger acid. Now the question arises, how can we know whether a conjugate base is stable or it is unstable? For the determination of stability of conjugate base, we will look on the groups attached to conjugate base. In second example, this is acetic acid. In both of first and two examples, you can see carboxylate ion C double bond O and CO negative is common. In the first example, with the carboxylate ion, hydrogen is attached, and in second example, methyl group is attached. In my previous discussion, I told you that hydrogen is taken as reference, so it means it don't have its inductive effect. And methyl group has donating inductive effect. And why it has donating inductive effect? That you can study in a topic of hyperconjugation. So when a methyl group is donating electron density, it means it is increasing negative charge on oxygen. So it means it is forcing this conjugate base to capture proton and go back to acetic acid form. Means there will be less number of hydrogen ions and the acid will be a weak acid. In first and two cases, if you are asked in your exam, compare the acidity of acetic acid and formic acid, your answer will be that in acetate ion, methyl group has electron donating inductive effect. It creates more electron density at oxygen and it will force acetate ion to capture proton and go back to reversible reaction, and there will be less number of hydrogen atoms. That's why acetic acid is a weaker acid, and in case of formic acid, hydrogen has no inductive effect. So as compared to acetic acid, formic acid is a stronger acid. Now we are taking a comparison of example 2 and 3. Acetic acid and fluoroacetic acid. We know that electronegative atoms have electron withdrawing inductive effect. So the arrow is showing that fluorine is withdrawing electron density from the oxygen and it's minimizing charge at oxygen and making it stable. That I mentioned at the bottom of equation number 3. Due to electron withdrawing inductive effect of fluorine, the fluoroacetate ion is stable and respective acid is a stronger acid as compared to acetic acid. Now come to the comparison of equation 3 and 4. What is different thing in equation 3 and 4? Equation 3 is fluoroacetic acid and fourth one is difluoroacetic acid. In case of difluoroacetic acid, when it goes into its conjugate base, in difluoroacetate, there are two arrows, two fluorine groups that are withdrawing electron density from the oxygen, and there is less negative charge in case of difluoroacetate as compared to fluoroacetate. So it will be stable and it will not go back to reactant, and there will be more number of hydrogen ions, and difluoroacetic acid is a stronger acid as compared to fluoroacetic acid. Now come to example number 5. In example number 3, 4 and 5, there is a gradual increment of one fluorine atom. In example 5, there are three fluoro groups and they are withdrawing electron density from trifluoroacetate ion in same direction, and there will be a very less charge on oxygen atom and its reversible reaction will be very slow because its conjugate base is most stable. That's why trifluoroacetic acid is the strongest acid that we have discussed so far. So if you arrange these acids, the strongest one is trifluoro, then difluoro, then fluoro, then formic acid, and at the last will be acetic acid. From top to bottom, only the number 2 will go at number 1 and number 1 will come at number 2. The last one is example to show you that inductive effect minimizes with distance. Inductive effect operates through sigma bond. You will also take another concept, that is delocalization, conjugation and resonance. Maybe some other resource person will deliver a lecture on that course. Resonance, delocalization or mesomeric effect, that is operated through pi bond. That is the topic we are discussing in this lecture. Inductive effect operates through sigma bond. Inductive effect minimizes with distance, while resonance effect, that maybe you have studied before this topic or you will learn that topic after this lecture. Resonance effect increases with distance. In the example number 6, there is a fluorine atom, but it has two carbon atoms in between carboxylate ion and fluorine. So when there is an increment in a distance, inductive effect will be reduced. That's why I have mentioned at the end of this equation that this conjugate base is stable. So very clear discussion has been discussed at the bottom of each equation, whether a conjugate base is unstable, whether it's a stable, whether it is a more stable or it is a most stable. So the sixth example is just to elaborate you that that inductive effect decreases with distance. The another application of inductive effect is description of bases. You have studied in your previous semester a concept that is Lewis base, Lewis acid base concept. According to Lewis, a species which can donate an electron pair is known as a base. So ammonia, it has a lone pair of electron. The two eyes are actually, I am not good in my writing at paper, so that's why it looks like a smiley. It's not a smiley, it's actually a p orbital loop and having a lone pair of electron. And the other thing why it get smiley, because I used a board marker to write on a paper. That's why it's looking like a smiley. It's not actually a smiley, it is a p orbital. So best acid, which one will be the best acid which can donate easily an electron pair? That will be a stronger base. In ammonia, there are 3 hydrogen atoms, and we know that hydrogen is taken as a reference. It has neither its donating or withdrawing inductive effect. It is taken as a reference. Second one is primary amine. It has one R group. R group stands for alkyl group. It may be a methyl, ethyl, propyl, butyl, whatever may be the alkyl group. It has one R group and 2 hydrogen atoms. It means it has one group that is donating electron density to nitrogen and increasing electron density on nitrogen atom and making it more basic as compared to ammonia. Now we go to the second example. Second example is secondary amine. It has its two hydrogens are substituted by 2 alkyl groups. In secondary amine, there are 2 methyl groups that are donating electron density to nitrogen and making it more electron rich, and it can donate more conveniently as compared to primary amine, so it will be more basic as compared to primary amine. So far the strongest base is secondary amine, then primary amine, and the least basic character will be found in ammonia. Now by taking the same discussion, we go to tertiary amines. It has 3 alkyl groups, so it means it has triplet effect of electron donation, and it should be more electron rich as compared to the previous three molecules, and it should be strongest base as compared to ammonia primary and secondary amines. But this discussion goes false in this case because there is not only one factor that is sufficient to describe any type of property of a molecule. When there are three alkyl groups, they make more crowd around nitrogen and they don't let any positive species to approach to central nitrogen as conveniently as compared to secondary amine. Although it's electron rich, but crowd around tertiary amine is much more as compared to secondary amine, and they don't let any positive species to come in close proximity to form a bond or to take electron pair from this molecule. So you might find another discussion that is about salvation. So in this scenario, the trend will be strongest base will be secondary amine, then tertiary amine, then primary, and the least basic nature will be found in ammonia. At the bottom, there are three heterocyclic molecules. One is pyrrole. Pyrrole is five-membered molecule. Next one is aniline, benzene ring having NH2 group, and pyridine. I have mentioned at the bottom of these three molecules, pyrrole is acidic in nature, aniline is basic in nature, and pyridine is more basic in nature. Why pyrrole is acidic in nature? Because nitrogen and hydrogen in pyrrole. Nitrogen is more electronegative, it can lose its hydrogen, and the lone pair on the nitrogen can easily resonate. Actually, I think so. These three examples should be discussed in a resonance topic. So, if I was I if a group leader assigned me the topic about resonance, then I will discuss these examples. Otherwise, you don't need to take these examples under the concept of inductive effect. You have to skip these three examples, pyrrole, aniline, and pyrimidine. Your topic is closed at the comparison of ammonia, primary, secondary, and tertiary amine. So stay at home, stay safe. God bless you. Allah Hafiz.